I'm Matt Manassi, Applications Engineer for the Integrated Signal Chain at Texas Instruments. Today I'm going to talk to you about ultrasonic transducers and ultrasound overview. We're going to step over here where we're going to work with transducers. But first we're going to talk a little bit about how ultrasound works. Ultrasound is any sound greater than human hearing in the range of 30 kilohertz to 10 megahertz. Looking at this diagram, ultrasound operates by having a piezoelectric transducer create an electromagnetic pulse into a medium that's created from electrical pulse exciting that transducer. That pulse then moves through the medium until it reaches an acoustic boundary. An acoustic boundary is determined by a difference in two medium with two different speeds of sounds. At that boundary, some energy will pass through the boundary and some energy will not. The energy that doesn't pass through is reflected back towards the transducer. The transducer then detects that echo and turns it back into an electrical signal. The TDC-1000 will then detect that signal and turn it into a pulse that a microprocessor can detect. Talking a little bit more about transducers, how do transducers work? Transducers are ceramic crystals that when you apply a voltage to them, they contract. Once that voltage is removed, that contraction stops and the expansion creates a pressure wave in the material that it's connected to. In this diagram here, we can see as the voltage is applied, the crystal contracts when there's a voltage present. That pressure wave then moves through the material to the boundary. Using a TDC-1000, I can detect those echoes and those pressure waves by being connected to a transducer. In this diagram, the TDC-1000 is excited by a trigger signal from a microprocessor. The TDC-1000 then produces two separate signals that indicate the beginning, the start, and the stop when the echo is received. This diagram on the lower left gives an overall view of the whole process. The processor's trigger, the start signal, the transducer excitation, the actual echo, and then the digitization of that echo. It's important to note here that what maximizes that return echo is a great difference between those two speeds of sounds of those two media. Now, in this diagram, we're talking about a single transducer method. This is called pulse echo, where a single transducer is both the speaker and the microphone. The TDC-1000 has the capability to use two transducers. There are some applications where you want to have one transducer as a transmitter and the other as a receiver, as is illustrated in this slide here. This transducer is the transmitter. The energy is transmitted through the medium and received by the second transducer. The TDC-1000, from its perspective, it's no difference. It gets a trigger signal that starts the process. It creates a start signal. It excites this first transducer, receives the echo, and turns that echo into stop pulses. Let's talk a little bit about the applications for this. A pulse echo application is best illustrated for level. In this case, I've got a non-invasive transducer mounted outside my container that's inducing energy into my medium, and at that medium air interface, I'm getting a returning echo. The TDC-1000, connected to an MSP430 or some other microprocessor, can then convert that into a time of flight calculation. With that time of flight information and the speed of sound of my medium, I can then determine the level or the height of that fluid in that container. The other application we can handle right now with pulse echo is fluid identification. Fluid identification is the same topology as a level. The only difference is I've moved my transducer from the bottom to the side. By doing that, I now have a fixed distance that my echo is going to transfer over. Looking at this equation here, the TDC 1000 will allow you to measure that time of flight, and if I know my distance, which in this case is this distance here, I can then calculate the speed of sound for the medium I'm in. This is useful for applications where I need to non-invasively determine what's in my container. This is helpful for some situations where materials are caustic or I don't have access to them. Now let's talk a little bit about the transducers themselves. We did an overall view of the transducers. Now let's look at some examples. Here on my bench, I have several examples of different types of ultrasonic transducers. What's important about the transducer for your application will be what is its key resonant frequency. For every transducer, there's two different types of resonances. In this slide here, for the frequency response of the transducer I just picked up, it actually has two key resonances. Every transducer that's shaped like a disc has two modes of resonance, a radial mode and an axial mode. Radial resonance is in the radial direction and not useful for this application. Our application here needs resonance in the axial mode. This is also referred to as the thickness mode on some specifications. Going back to our transducer selection, transducers come in different sizes. The size of the transducer will determine a few things about your application. For the demo today, we're going to use this 1 megahertz transducer. Looking closely at this transducer, there's two parameters that we're really going to be interested in. The radial width is going to determine the radial frequency. The thickness of the transducer determines its axial resonance. In this case, this transducer's axial frequency is 1 megahertz. A few of these other transducers we have here have much larger radial sizes, and some are smaller. Why would one transducer work better than another? The radius of the transducer is equivalent to its sensitivity and its power. In a nutshell, the larger the transducer, the more power it can send into your material and the more sensitive it is to those echoes. A medium-sized transducer, medium-sized sensitivity. Larger transducer, much more sensitive. The last problem you have to solve for your application is which size is going to work best for you for that cost. A larger transducer is going to cost more money. Lastly, speaking of transducers, depending on your application, if you needed a fully waterproof system, you'd buy a transducer like this one. You might want to use this type of transducer if it's exposed to water or other chemicals. The downside to this is it's much more expensive because of the housing, the acoustic dampening, and the attached cable. What we're going to talk about in this demo is how to utilize these inexpensive transducers to measure level and fluid identification for cost-sensitive applications. We're going to go through the process of how to mount this transducer directly to your container with a simple multi-step process. Let's go through that now. First, let's start with our container. This is an acrylic container. In general, acrylic is not very easy to adhere things to. The key to making your transducer stick to this is preparation. It's a two-step process, and what we need to do here first is roughen up the surface. It's plastic, luckily, so I can take some simple 800 grit sandpaper and rough up the area that's just as big as my transducer. Next, I need to degrease that. any kind of oils will reduce the glue's ability to keep that transducer on that flexible surface. I'm going to do that now with a couple of drops of alcohol. I'm then going to use air to dry the surface. Now I have a clean, degreased surface that's ready for adhesion. Let's talk a little bit about glue. What does this glue need to do? The purpose of this glue is to maximize the connection between this transducer and the wall of my container. I can't afford to have an elastic glue because an elastic glue acts like an acoustic resistor. It dampens down any energy going into the container or being the echo received. So I need a glue that's stiff, but too stiff would be a problem as this is a flexible material. So, to attack that problem, I'm using cyanoacrylate. Most people know it as crazy glue. This is a specific form of crazy glue because it has the latex added to it, which allows it to be slightly flexible, so as the container flexes, the glue doesn't shear off. The other thing that's really useful about crazy glue is it starts out as a liquid, and when it cures, it becomes a crystal. So it's the best of all worlds because it's incompressible, and all of that ultrasonic energy makes it through the glue into the wall and into your medium. Let's glue this transducer on right now. You only want to apply just enough to cover the transducer. Next, you want to make sure your position of your wires or your transducer is appropriate to your application. And applying a small amount of pressure so I maximize my contact to the container. Now, let's use one of the other benefits of crazy glue. Crazy glue being a liquid to a crystal, that curing process can be accelerated with accelerant. Apply the accelerant to the glue to cure it. Just wait a few seconds, where what normally would take about 10 or 20 minutes, I can speed up your assembly process. While still maintaining pressure, blow off the excess. Lastly, we'll need to clean with a few drops of alcohol. Again, using air to blow it off. Now I've got a transducer mounted to this container and ready to sense, in this case, fluid identification applications. It's an important note to make sure that you actually glue it onto the container. We've had some folks that have tried less effective methods, taping, etc., or using rubber glues. They'll just take away from the energy that gets put into the container and you won't be able to receive your echoes. Glue is the key. Some other things you can do, depending on how good your transducer is, acoustic dampening on the back of the transducer. For this example, I didn't need to because this transducer is very efficient. It's a larger transducer. In the case of trying to detect a signal very close to my transducer, every one of my transducers, when I excite it, they ring. This, in your transducer specification, is called ring down. By applying an absorptive adhesive to the back of the transducer, I can minimize that ring down. Which adhesive you use is a function of what you have time for. In this case, I was in a hurry, so I just used hot glue. Hot glue is very sticky and it takes no time to adhere. The other alternatives are RTV. They could take up to 24 hours to cure, but are going to give you the maximum dampening capability. So far we've talked about how to put together a fluid identification system. We can turn this fluid identification application instead into a level application by merely putting the transducer on the bottom of the container. Well, that's it for this video so far. Please go to the following web addresses for more information, and thanks for watching.